Next slide. Okay, so yesterday, if you don't remember, we talked about neural networks, how they work in specific. So, okay, wait, first we talked about generative AI a little bit, uh, supervised, unsupervised, all those types of learning. So supervised learning is where a machine learning model learns from labeled data, and then unsupervised learning is when AI learns from normal data, so data that isn't labeled. Reinforcement learning, semi-supervised learning is when there's a small amount of labeled data that the AI learns with and a large amount of unlabeled data. And then reinforcement learning is where the model gets either rewarded or punished for making decisions. And then there was generative AI, which has the ability to create new content. And you can't guarantee that it's accurate, by the way. And then it's different from traditional AI because it actually learns from information, creates new content. Here are some key takeaways of generative AI. It creates new content, it needs lots of data, it sees patterns. So examples of generative AI are like ChatGPT, Siri, Alexa. And then we went to deep learning. We talked about what deep learning is, which is a branch of machine learning. So it's technically also a part of AI and it involves neural networks. Then we talked about neural networks and how it was created to use this speech pick. And then we talked about how it works specifically. And this is a diagram. Each one of these dots are neurons, and each one of these lines are connections between the neurons. We talked about the different layers, how that works, how details are analyzed uh, upon other details. So we talked about this image, for example, and how 0 is black, and then any number other than 0, well, I mean 0 is white, any other number that's not 0, the higher it is, the darker it is, and how each pixel is counted as a neuron. Then we talked about what the depth and width is. And I think we left off here. Okay, does anyone have any questions about yesterday? No? Okay. Then we'll start for today's content. Okay, so this is just like a little bit of expanding on neural networks. We already talked about like pretty much all of it yesterday, but I guess this is just a little more information. Okay, so our brain's internal system is a web of billions of neurons. And the way it works is fascinating. So, as I told you, this is what neural networks were modeled after. They were modeled after these neurons in our brain. So, scientists observed these patterns to create neural networks which drastically improved their capability of AI. Essentially, neural networks are like complex puzzles made of tiny pieces called neurons, just a summary of yesterday. And these puzzles can learn from examples and solve problems by connecting these neurons in various ways, just like how our brains learn and figure things out. We talked about this yesterday, of course, but this is just a more simplified meaning. You can choose to take this in, but also keep in mind the stuff from yesterday. Go there yet, actually. But why is neural networks more capable than simpler forms of AI? So neural networks are a lot better and a lot more advanced and a lot more capable than simpler forms of AI and machine learning because they are great at recognizing those smaller details and analyzing things very deeply and thoroughly. Like I talked about yesterday, first we may have noticed an island in the background, and then on the island there was a building. Just like analyzing those really small details, looking at everything in the picture, and thoroughly like connecting everything together. So with their web of interconnected points or neurons, they do this. So they connect everything together, and this makes them better at solving complex problems and recognizing patterns in data. So I told you earlier, generative AI sees patterns, and generative AI uses neural networks, and neural networks is what allows generative AI to see these patterns. So, does anyone have any questions? And then we'll move on. Okay, so NLP or natural language processing. What is it? So, natural language processing, or more commonly known as NLP, is a field of computer science that studies how computers, specifically AI, understand, interpret, and generate human language. So NLP came to life around the 1960s. It wasn't very advanced, wasn't very good, but it came to life around the 1960s. And in the early days, the first NLP methods focused on rule-based systems, so conditionals. And if, so for example, actually, I'll just say the examples later, but for now, they use language grammar rules to try to process the text. So, for instance, in designing such a system, I might establish a rule that says you have to treat sentences starting with can you, or will you, or is it as questions. So, any sentence that starts with these three starting phrases, I guess, I would instruct the AI to recognize these as a question. So this process doesn't require any machine learning or neural networks of any kind because the machine isn't actually practicing and learning with data multiple times. It's simply just following the explicit instructions that we give to it. So it's also a lot easier for the computer to do this, and it will follow the instructions correctly. It won't ever mess up. But there are a few scenarios in which our instructions may be lacking or wrong. Because these are not the only phrases that questions start with. So anyway, this rule about questions, can you, will you, is it, this seems quite basic and manual, doesn't it? So, in the late 1980s and especially early 1990s, statistical NLP emerged, making a shift from rule-based systems like this one uh, to an approach involving probability that interprets language data through extensive data analysis. So there'd be a bunch of like data scientists and people who analyze the data, and they will be trying to find parameters or rules that AI can follow. Okay, so in the 90s, a statistician might have been tasked with designing a program to identify whether the word can, so this right here, not the noun, is used as a noun or verb in a sentence. So in this scenario, in this first sentence, it's used as a verb. So the difference is very important because as a verb, can describes, well, can describes a person's ability to do or accomplish something, whereas as a noun, the word can refers to like a cylindrical container, so a Coca-Cola can that you've all probably heard of. So this would allow, okay, so back in the 90s, I would have to gather many sentences containing the word can and make annotations to whether the word was used as a noun or verb. So yeah, like this, for example, the word can would be a noun because can of soda. Can is an object, like a cylindrical container. Here, in both scenarios, can are verbs. So I would have to go through a lot of data and label each can as a verb or noun. That obviously would take a lot of time because LLMs, which we'll talk about later, but generative AI in general, ones that use NLP, they need a lot of data. Uh, Hundreds of gigabytes of data is what they require. And going through all of that labeling all these sentences, that's gonna take a lot of time, which is a big downside. But this would allow me to perform a context analysis by analyzing other words that can was used with. So for example, the analysis might reveal that when words like you or I are close to can, so can you, I can, when they're close to can, it typically indicates a verb. Alternatively, if words like soda are used in the sentence, like over here, it probably refers to the noun. So, like a Coca-Cola can. So the final goal of this analysis is to obtain a model, a machine learning model. So you can also call that an AI if you want. And the goal is to make the model capable of indicating the probability of whether can is a verb or a noun in a given sentence. So with this sentence, the AI should be able to find out if this is a verb or noun, which it's a noun. And in these two sentences, it should be able to recognize these two as verbs.
Don't they? I have a question. I have a question.
Yeah.
So, when it's trying to make the AI differ between the soda can and the question can, the noun and the verb, will it like teach it like the grammar or something?
Yeah, so like in the early 1960s, like rules for grammar, like you have to put like a period at the end of the sentence, how words connect together. They were all given to machine learning models. Obviously, not all of them were given because that would take a long time. And it wasn't very advanced. But yeah, AI would usually know some grammar, at least. Other questions?
I have a question.
Yeah, ask.
How how do you make it like how do you make it differ between the noun can and the verb can? Like do you just point out the words before the cans, or do you just fix it?
Yeah. That's a really good question, and that is what I'm going to be talking about like a little bit later. But yeah, it looks at the surrounding words or the context, and it tries to figure out whether it's a noun or verb. So yeah, you're right. Like it does like look at the words that come before, the words that come after, all the words. And I'll be talking about that a lot more specifically, like a little bit later. So we'll just like continue for now, and then I'll talk about it a little more in depth.
Wait, I have a question.
Hmm.
Would this be 100% accurate when differing between the verb can and the noun?
Well, I mean, for modern AI like ChatGPT and stuff, you can probably like expect it to be like 99.999% correct. There's always like the 0.0000001 chance that it's incorrect, but you're never gonna see that. But in earlier forms of AI, like in the 1900s, you couldn't guarantee that it would be 100% accurate because they weren't able to be like trained on much data since there weren't that many big computers that could hold that much data. So they weren't that accurate, they weren't that efficient. Any other questions? All right, then we'll move on. So the final goal of this analysis is to obtain a model capable of indicating the probability of whether can is a verb or noun, like I just said, in a given sentence, based on the frequencies and connections um, to the context calculated earlier. So these surrounding words. So attempting to find patterns in the data in this way are this is similar to the most primitive and basic forms of machine learning. Machine learning in its modern way is way more advanced and involves a lot of math. this is very primitive and basic. So using conditionals like this is in this barely flexible manner is not at all what complex machine learning models use. And when I say conditionals, I mean like rules like this. So if there is can you in a sentence, if there is will you in a sentence, if there is in a sentence, those are conditionals. So NLP algorithms work by breaking down the text into smaller components, like for example, let's say what is that? Okay. Let's say that you start with a page. Okay, okay, so like let's say you start with a book. Then it would break it down to pages, then it would break down those pages into paragraphs, and break down those paragraphs into sentences, and break those into phases, and break those into words, and those into letters, and just break everything down as much as possible to go through each part individually and make as much sense of what it's reading or analyzing as possible. So it analyzes these components using various techniques and mathematical operations, and then applying machine learning models to find meanings and perform specific tasks. These algorithms analyze the structure and meaning of the language, allowing machines to understand, interpret, and generate human language. So I just said generate human language. This indicates that this is generative AI that I'm talking about. Okay, so we won't go too in depth into this yet because this involves some trigonometry and some other complicated math, and I don't expect any of you to know that. But we'll move on for now. Okay, what is an LLM? I know most of you probably don't like reading paragraphs off of like slideshows and stuff, so you can just listen to me and I'll kind of summarize it. So an LLM or large language model is a type of generative AI that specializes in understanding and generating human language. So it learns from huge amounts of text data to write stories, answer questions, and even have conversations, like a smart helper for language-related tasks. Like most generative AI, LLMs use neural networks too. So and one example of an LLM is like ChatGPT. So, have you ever had a conversation with ChatGPT? Because it almost seems to talk to you like a real person. So, the purpose of ChatGPT isn't to like generate images or audio, but to generate text and engage in conversations with the people that use it. So, LLMs are just like they just specialize in language, so they can talk to you, they can uh, understand what you say, they can have conversations with you, and they can communicate with you using language. So why is it called a large language model though? Large is underlined here, so you probably see that. But LLMs are called large language models because they need a large amount of data to learn from. And by large, not just large, but enormous amount of data to learn from. LLMs take in hundreds of gigabytes of example conversations to accurately learn human language. So I told you ChatGPT took 570 gigabytes, which is a lot of data. Okay, any questions about LLMs right now? All right, I guess we'll move on. Okay, wait, not yet. So what are the features of LLMs right now? So these are the key takeaways too. But LLMs can grasp context. So they're great at getting context from surrounding words, making them effective for tasks like answering questions and writing naturally. So they can also remember what you said from your previous words as stated here, which is just the same thing as getting context from surrounding words, but like a little different. And they can understand non-explicitly stated things with this context. So let's say you and I are having a conversation, and I say, Elon Musk is very rich. And then you say, you're right, he is very rich. So if you talk to AI about that, it will remember that you said Elon Musk is very rich. and when you and it will say when you like respond to he is very rich, it will know who he in that sentence is. It'll connect he with Elon Musk. So it'll understand that I'm saying Elon Musk is very rich. So that's how it grasps context. So for a basic AI, if we give it some information to do some task, if we ask it to do another task, it won't remember the information we gave it instead, earlier. Instead, it would completely reset and start brand new. But LLMs are not like this. So LLMs remember what you said from previous prompts. So LLMs can understand human language. This is probably the most important thing, obviously. It's called a large language models. They can understand and generate human language, and they use NLP algorithms like I talked about earlier. So LLMs also require a lot of data to work efficiently, which is why they're called large language models. LLMs train on hundreds of gigabytes of example conversation, so they also need a lot of computational power to store that data, to like learn from that data. And finally, LLMs are very adaptable. This is something I didn't specifically talk about this yet, but LLMs are usually not only trained on example conversations, but also on data from the internet. So due to this wide range of knowledge, they are very adaptable and can quickly shift topics. Because obviously on the internet, there's a lot of information that you get, and there's a lot of different topics that you can talk about. Okay, any questions about this?
Oh, I have a question for.
Okay.
I forgot to ask the last slide, but for LLMs require a lot of data to work efficiently. How big is exactly like 1 GB of data?
1 GB. Okay, so do you know what kilobytes are or any of that? Wait, actually, okay. I think I have a good way of explaining it. So, um, 1 second. Okay, so an average computer would be able to store 500 gigabytes in total, and it would be completely like full, like completely loaded. And your computers that you're probably on right now, like if you're on a computer or if you have a computer or something, they probably have lots of like different apps like Google or I don't know, like Safari or something if you're on Mac, like Microsoft Edge. The point is they have a lot of apps and that takes a lot of data. Since Google like on itself is pretty pretty important. And you have access to the entire internet. You have all your data and stuff that you store. And the point is your computer can hold a lot of data. So it's usually around 500 gigabytes that your computer can hold in total when it's completely full. And so ChatGPT was trained on more data than that, which is a lot of data. So just to put it to reference, that's how much I'm talking about. Okay, any other questions? All right, then we'll move on. Okay, so now we'll carefully study how LLMs work. Okay, so for this, I'm gonna use a simple example, as you can see here. So let's say there are 4 kids, maybe even including you. They're playing a team-based word association game with your friends. Don't be intimidated by team-based word association. I'll break it down. Do you have a question? Okay. So first, 4 players are divided into 2 teams. The people on the left, A and B, they're one team, and the people on the right, so C and D, they're one team. So player A would whisper a secret word to his opponent. So the person on the other team, player C. So player A would whisper any secret word to player C. And next, player C would then have to say a related word out loud to player D. And player C, well, wait, no, player D has to guess what player A said to player C. Okay, this is kind of complicated. But they have to guess the original whispered word, and player D gets one guess. So for example, okay, say that player A whispers banana to player C. So A says banana to C, and C has to help his teammate D to guess the word banana. So he has to say a word that's related to banana. And a word that's related to banana is, for example,
Yellow fruit.
yes. Well, it has to be one word in this scenario, but yeah, you can say like yellow or fruit. So, okay, let's take yellow since there's a lot of different fruits, and yellow is more closely associated with banana. Wait, 1 second. What just happened? Okay, so let's say that player A whispers to player C banana, and then yeah, player C says yellow to player D. So player D, with the hint of yellow, might associate the two and guess banana. So he might successfully get banana, and his team gets a point. And that's a victory for player C and player D's team. But there is also a chance that he guesses the word wrong. There's always a chance he guesses the word wrong. The color yellow could be associated with lemons, sunflowers, the sun, or taxis, along with bananas. If he guesses it wrong, his team doesn't get a point. So in this scenario, he guessed sun, and he guessed the word wrong from the hint. So basically, what this game is player A is whispering banana to player C. Player C has to give a hint to player D with one word as to what it is. Player D is supposed to guess what player A said to player C. So player D in this case has to guess banana, but he guessed it wrong. He guessed sun in this scenario. So instead of saying yellow, the word peel would be a better word to describe bananas, as bananas have peels, and this is what peels are most commonly associated with. So if player C said peel instead of yellow, player D would have probably guessed banana correctly.
What about orange?
Yeah.
Wait, what do you mean? Like if player A said orange?
No, if player C said peel, couldn't player D guess orange? Because oranges have peels too.
Yeah, okay, so the goal of this game is to just say the word. Okay, so player C has to say the word that's closest, like closely related to banana. And most commonly, like if you search a peel on Google, then you'll probably get, oh wait, never mind. Okay, wait, peel, drawing. Then, yeah. If you search
When
for
I
peel
was-
drawings, like almost everything is a banana.
When I searched it up, it literally gave me an orange peel.
And
Okay,
also,
well,
wait, I have a question.
yeah.
Why couldn't have player C said peely?
Huh? Can you repeat that?
Peely.
Peely? Oh, like the guy from Fortnite, you mean?
Yeah.
Who's that?
Oh, I mean, yeah.
Oh, it's like a
you can Google it.
banana guy. It's a banana guy.
Yeah, you can Google him if you want. But yeah, that would actually be a really good hit. Like that, player D would almost certainly guess it. But okay, so in general, the point is player C has to say something related to to the word that they say. So let's say that player D got it wrong, then it would move to player B. So let's say player D got it wrong, then player A would again have to say a related word to his teammate, and his teammate would have to guess the word. And if he guesses wrong, it goes back to this team. If he guesses it wrong again, it goes back to this team, and back and forth until someone guesses it right. So let's say player B's team guessed it correctly. He guessed banana from the hint yellow. So anyway, in the end, to be good at this game, you have to be able to think of a word that maximizes the probability of your teammate guessing the word correctly. So in this case, player A thought of the word yellow to help player B guess the word. So some words may be too complicated, so you'll need a few tries to understand them, providing more context and more related words for you to get. So let's say I'm player D and my teammate. Okay, wait. Let's say that player B's teammate first gave him the word citrus. And citrus is most commonly associated with oranges. I mean, it's in other fruits too, but it's mostly associated with oranges. So player B would guess oranges, and that's not correct. Grapefruit is the correct answer. So it goes back to player D, and then player D guesses it wrong. It goes back to player B, and then here player A says bitter, and then bitter and citrus. Player B successfully guesses grapefruit. So sometimes you might need a few tries to guess the word. So alternatively, saying citrus and pink also have a high chance of success instead of saying bitter. So the first prompt has a low chance of success. The second one has a high chance of success. Okay, so the reason I'm talking about this game is to give you a very important lesson. Context is crucial. So why do you need to know this? Why have I told you this game again? This is an excellent analogy of how language models, including LLMs, operate. A language model primarily predicts the optimal word to fill a blank space based on its information. So here, based on the information, so based on the hints that were given to player B is able to guess grapefruit. Similar to that, LMs or LLMs are given context. So context, and with that context, you can use it as hints and it's supposed to guess the word. So let's take this example sentence. Can everybody type in the chat what they would fill here? This should be pretty obvious, but like, yeah.
Wait, what did you say? I'm sorry. I didn't follow.
It's fine. Can everybody type in the chat what fits in the blank? Okay. I can see that what I can see that mostly everyone is getting it correct, thankfully. But the name of the planet we live on is Earth. The correct answer was Earth. The name of the planet we live on again is Earth. We know this because we have the knowledge of the planet we live on, at least most of us, thankfully. If we didn't, that would be quite concerning. But that's how a machine learning model, specifically a language model, works. It predicts the optimal word to fill a blank space based on the surrounding words and context. So this, the name of the planet we live on is this phrase, like not including the blank, this is what is being taken as the context. Context is key. Without context, not only language models, but we wouldn't be able to predict what fits the blank with certainty. So let's say that your math teacher walked up to a whiteboard. All she wrote down is a blank, and she didn't even give you any information. And if she told you what fits the blank, wouldn't you be puzzled? So she just walks up to the whiteboard. All she writes is a blank, doesn't even say anything else, and just says, fill in the blank. You wouldn't even know what the question is. You would be completely bamboozled. You'd be puzzled, and you wouldn't know what to do. So you need the context, the information to answer the question. And so does so does a language model. A large language model, just a language model, any language model. So that's how a language model analyzes context. So for example, have any of you heard of this quote right here? Okay, wait, not this one. This quote.
Question.
Yeah. Question is the missing blank thing. But this is
I heard
like
the
really
first-
famous.
I've heard the first part, but the last part I could just infer it.
Yeah, because like it gives you two options and it says that is the okay, yeah, question would fit. You're right, you're right. Okay, so I'm for now assuming you heard of this quote. If you didn't hear of this quote, that's also okay. But this is a famous quote from the Hamlet by William Shakespeare. And all of you have probably heard of Shakespeare. He was a playwright, and if you didn't, that's also fine. You don't need to know this for these classes, so that's not that important. But anyway, the correct answer is question, as already said. If a language model had knowledge of Shakespeare or of this quote, then it'd know what fits in the blank of the quote. Based on the context, it would fill in the blank as question. So, like in the word association game, the language model, like the player guessing the mystery word, fills in the blank with the most probable word based on the related words or context that was given to it. So, if you didn't like know that this was by Shakespeare and like you've never heard this quote, there's a lot of different words that could fit in this blank. And you would try to pick the word that has the most probability of being in this blank. And that may be question, or that may be like choice or something like that. That may be decision. I don't know, but what language models try to do is they try to predict the most probable word and they put it in the blank. So language models are probabilistic, capable of predicting the missing word in a sentence based on the context provided by the surrounding words. Okay, so we generally have two types of language models, masked and autoregressive. After this, yeah, masked and autoregressive. Okay, so here we have masked language models. They guess the missing word no matter where the missing word is located in the sentence. So, for example, let's take this sentence. Water blank at 0 degrees Celsius. Oh, I spelled degrees wrong, but that's fine. In this case, the masked model could use the information before and after the blank space to fill in the missing word. Can everyone in the chat like type what they think it is? And it's okay if you don't know, honestly. Like, it doesn't really matter for these classes, but give it your best guess. And if you don't know, like, at all, then you don't have to type it in either. Okay, I see that most of us got it right. Okay, and Avik, you're also right in a way, yeah. I guess that we could say that you're right, but a synonym for that is freezes because it's supposed to be one word, but your answer is also acceptable for sure. Okay, so the answer here,
Wait, isn't it supposed to be word, not phrase?
what?
Isn't it supposed to be word, not phrase?
Word, not phrase. Yeah, it's one word. So freezes. But I didn't specify that ahead of time. Like your answer is also completely acceptable. So anything that like fits the definition would be correct. So yeah, your answer is also right. Okay, so I see that most of us got it right. Water freezes at 0 degrees Celsius. And again, I spelled degrees wrong. Don't mind that. But in this case, the masked model could use the information both before and after the blank space to fill in the missing word, which is going to be freezes. And meanwhile, autoregressive models guesses they guess the next word in the sentence. not the middle word, not the first word, but the next word. So the final word in the sentence. It goes in order from left to right, goes like that to guess words. So let's take the same sentence, but like a little different. Water freezes at 0 degrees blank. Here, the autoregressive model will be able to predict that the next word in the sentence is Celsius. OpenAI's models are actually all autoregressive, and OpenAI, by the way, is the company that created ChatGPT, if you don't know. But all of their models are autoregressive models. And they work by conditioning each prediction on all the previously generated words. So they only look at the words that come before the blank, and they guess that word. But how can language models predict the next word in a sentence? This is rooted in statistical learning from vast amounts of data. Like I said, language models take in a lot of data to work properly. So a language model gains the ability to work with language by analyzing and learning from the patterns and structures found in the given text it processes. So this involves learning from and absorbing large data sets containing many different language styles and uses, which allow the language model to recognize and predict word sequences in many different contexts.
So essentially, what you're saying is that so if we have water freezes at 0 degrees, then with its prior knowledge, it's going to like say that it's 0 degrees Celsius, right?
Yeah, what the knowledge it has, that's right. And um, to fill in the blank, obviously, it should already have the knowledge that water freezes at 0 degrees Celsius, and all this data is pulled from the internet. So ChatGPT, like I said, a lot of times was trained on 570 gigabytes of data from the internet, and that's how it knows all it knows, which is a lot of stuff. So over time, the model builds a probabilistic map of word associations and dependencies, improving its ability to generate logical and contextually appropriate responses to like more complicated prompts and questions. So the outputs of language models are open-ended, and that means that they can use the vocabulary built from learning from training data to generate an infinite number of possible outputs. There's so many combinations and actually an infinite number of combinations that you could use with the English words to create different sentences or paragraphs, phrases, whatever. Okay, so the word generate is key here, hence the name generative AI. All language models are examples of generative AI. Okay, so initially, AI developers focused on creating language models that only work with one single language, but modern models like ChatGPT are capable of processing and understanding multiple languages. So generally, when we discuss language models, the focus is often on LLMs or large language models. But clearly, what distinguishes LLMs and LLMs is the size. But what size is enough to consider a language model as large? The term LLM actually doesn't have a clear definition and can be used quite flexibly. So you could technically call anything you want an LLM, like any language model, no matter how small it is, but commonly it's used for models that have relatively a large amount of training data. So the term the term large language model again reflects the training on enormous amounts of data, and this enormous amount of data continues to further expand over time. So the differences between LMs and LLMs is that LLMs are trained on a lot more data. Okay, now I don't know if you caught this, but I just said that the amount of data that LMs and LLMs alike are trained on continues to further expand over time. What am I talking about? So what is deemed as a large amount of data today probably won't be in a few years. For example, GPT-3 was trained on 175 billion parameters. And then next came GPT-4, which was trained on over 1 trillion parameters. And GPT-5 is likely to use even more. And as you can see, the number of parameters it's being trained on, it is increasing by a lot, multiplicatively. So it's believed that the richer the training data for LLMs, the smarter and more versatile they become. Okay, so now that we've talked about how LMs and LLMs work, let's talk about how they learn. In supervised machine learning, we provide labeled data to the computer. It always has to be complete labeled data. And for example, let's say we wanted to train a model to distinguish between positive and negative customer reviews. We could get a data set of 100,000 customer reviews and manually label them as either positive or negative. The computer will then use these labels and learn how to categorize new unseen reviews as positive or negative. Okay. So, one second. Okay, so the drawback to labeled data, as I have said earlier when talking about supervised learning, is that it's very expensive and very time consuming to label data manually. Like one person or even a few people, they have to go to like through over 100,000 different pieces of data and label them each on their own. That is going to take a lot of time, and you have to pay them to do that too, which is going to be very expensive. So if categorizing one single review as positive or negative costs 30 cents, we must pay whoever like categorizes all 100,000 reviews $30,000 to classify the entire training data as either positive or negative, since there's 100,000 different reviews. Clearly, that's a lot of money. So categorizing one review is fairly simple, but categorizing 100,000 of these is going to be difficult. Can you imagine how much more difficult it would be to categorize more complicated things like medical records, articles, novels? It would also be a lot more expensive and very time consuming. And especially if one person had to go through more than 100,000 of these, and each one costs $30, the total price would be over $3 million. So one review of medical records probably wouldn't cost 30 cents, but $30 or more. And like I said, there was just 100,000 times 30 is 3 million. And that is a lot more money than reviews. And a lot of models are trained on a lot more data than just 100,000 pieces of data. Imagine how much more that would cost to train. So therefore, we can conclude that supervised learning has significant limitations in terms of labeling large amounts of data. So the cost increases exponentially with the complexity of the data fed into the model. So people often say that ChatGPT was trained on the entire internet. Can you imagine how much work would be needed to read and label the entire web? Like, it's unimaginable. It would cost so much since the internet is absolutely enormous, and it would most likely take many, many, many years since the internet is actually still growing at a very fast rate. In fact, it would probably never be over. So, how does that work then? How was ChatGPT trained on the entire internet? So, LLMs need a slightly different approach to train because this is very, very, very time consuming and extremely expensive. So the other obvious option is unsupervised learning. Again, this type of ML, does not use labeled data, it uses unlabeled data. So it operates without labels and it seeks to discover more about the given data without any additional information or feedback. So there's just raw data like raw text files, raw images, raw records, for example, but there's no description of it, so it has to learn on its own with the knowledge that it already has. So with this approach, there isn't a clear objective without a specific goal when everything is just random and unlabeled. It's challenging for the model to learn structures that help it understand or generate human language. Moreover, language is a form of expression where context matters significantly. Words in a single sentence can create context, and each paragraph builds upon the last to enhance it further. And that's a lot of context based on what LLMs are reading, because 570 gigabytes of text data, that's a lot of data. And you probably would take several days, okay, definitely more than several days, like probably like months to read that all. I don't know, but it would take a very long time. And the amount of data is actually still growing. Like I said, it's expanding over time. So imagine how much more difficult that would be. But the problem is that, again, unsupervised learning does not give importance to predict the next word from previous context, meaning that it may overlook subtle, like subtle but important differences in language. So essentially, if you use completely unsupervised learning for a model like ChatGPT, the AI just becomes brains. Like it's going to be absolutely useless. It's not going to be very good at all. And that is obviously something that engineers at OpenAI and pretty much anyone, they wouldn't want their model to be dumb. ChatGPT is like supposed to be a breakthrough. It's supposed to be really good. So we need a machine learning approach that self-learns and it predicts contextually and automatically generates labels. We need a balance between supervised learning and unsupervised learning. And there is a solution to this actually. And that is called self-supervised learning. This was the breakthrough that led to the creation of LMs and LLMs. So this analyzes text databases, it automatically generates labels, and it predicts following content based on context. Again, this is probably like the 10th time I've said this. Context is key. Context is important. Without context, we can't predict anything. So this hybrid approach allowed for the creation of models like ChatGPT, DALL-E, Gemini, and it also improved their ability to understand and generate human language in a natural and aware way. Okay, that was quite a lot of information. Does anyone have any questions? All right, it doesn't look like anyone has any questions. Uh, before moving on to the next section, I think we'll just stop here at this like milestone kind of thing. Can everyone type in the chat what was the most interesting thing they learned today? And also, if you have any questions, again, don't be afraid to ask. If you're feeling uncertain, uncertain about anything, it said self-supervised learning. Yeah, like self-supervised learning is absolutely revolutionary. It's very important. That's a good answer. LMs, yeah. So there weren't just LLMs, LMs. Yep, and Derwin said that too. Okay, I guess pretty much everyone is saying that, and yeah, that is really important and really interesting because they can have conversations with humans. They can communicate human language. Okay, Avyuk said how to balance unsupervised learning and supervised learning. Yeah, and that was a problem, but now with self-supervised learning that is solved. So yeah, that's also an interesting thing to point out.
Wait, I have a question.
You can ask.
Is semi-supervised learning better or self-supervised learning?
Um, probably self-supervised learning, especially for these like big important models like ChatGPT or Gemini or DALL-E. Self-supervised learning is what was used to create them, so you you can say that self-supervised learning is probably better, but when training like small models that don't have much data, semi-supervised learning is always a good option, and it's probably better too. Or supervised or unsupervised learning, these are probably all better options. But only with the biggest models like ChatGPT and stuff, self-supervised learning is definitely the solution. Okay, Kashyap said that the most interesting thing I learned was that the computer has some component of it that can A, predict words, and B, fill in words with all its data, all with its data. Yeah, that actually is something that like we didn't talk about. And it's a good thing that you did notice that, since it's very interesting. And normally we might have talked about that, but like if you start to go more in depth into that and like think about everything that's actually involved in it, it is very, very, very advanced, very complicated. There's lots of complex math involved with it. And we're not going to take the time to learn that, since you're probably going to like learn that sometime later in school or in college, and that's simply way too advanced. Also, that would eat up a lot of our time.
I have
Okay,
a question.
you can ask.
It was for last week, yesterday. Did I miss anything from yesterday?
Yeah, you did miss a few things about neural networks. Um, you can look at the WhatsApp group, or I think like Deepali is posting some like recordings of the classes on YouTube, and she'll share them with you too. So just keep an eye out for that, and you can listen to the class recordings. There was some pretty intuitive things we like learned yesterday, some like important things. So I recommend you do take a good look at that since you weren't here yesterday.
Sure.
All right then. Looks like everybody has responded. Um,